we define a recursive sequence. The an plus 1 is equal to an plus 1 over the kth root of an. And we let a1 be greater than 0, where k is a positive integer that's greater than 1. Then what's the limit of an to the power k plus 1 over n to the power k? If an has a limit, or is bounded, then this limit is obviously 0. So I'm guessing an is most likely tending toward infinity. Here, because I notice n plus 1 minus an is equal to 1 over the kth root of an, which is obviously positive if you use mathematical induction. So immediately I have an is a increasing sequence. Right? So therefore, an is greater than or equal to a1. So, because according to this, a2 minus a1 should be equal to 1 over the kth root of a1. a3 minus a2 is equal to 1 over the kth root of a2. an minus 1 is equal to 1 over the kth root of an minus 1. Since here, I take the reciprocal and take the kth root, it has to be less than or equal to 1 over the, this is the same, this less than or equal to 1 over the kth root of a1. All the way less than or equal to 1 over the kth root of a1. And so when you add them up, you have an minus a1 is less than or equal to n minus 1 over the kth root of a1, which is less than n over the kth root of a1. Right, so maybe let's rewrite it as some positive constant times n, I denote it as a. So an is less than or equal to a1 plus a times n, which is equal to n times a1 over n plus a, which is less than or equal to n times, replace n with 1, a1 plus a, denoted as b times n. B is some positive constant. So, meaning, if we can somehow show that an tends towards infinity, still we would have an is not tending toward infinity too quickly, because it's less than or equal to some positive constant times n. It cannot tend toward the infinity at the greater speed than n, such as n to n squared or n to the power 3, something like that. So next, how do we know that an tends towards infinity? Right? It's because from this we can say that 1 over the kth root of an has to be greater than or equal to the some positive constant c. I denote it as c, kth root of n. So from this, we can immediately use the same technique as here, right? Add them all up, then use the inequality. Then an minus a1 has to be greater than or equal to I from 1 to n minus 1. Constant take out. C. Here's 1 over the kth root of I. Right? And each time I use I here. So I goes from 1 to n minus 1. And remember, if we have I from 1 to n, I from 1 over I to the power of p, as long as p is greater than 1, then it is convergent. If p is less than or equal to 1, it has to be divergent. So here, p is equal to what? 1 over k. K is greater than 1, so this has to be less than 1. So it has to be divergent. Not only divergent, but also tending, it's already greater than the harmonic series. It has to be tending toward infinity. Just plus this A1, it doesn't matter. So tend toward infinity. Now we've really shown that AN really tends toward infinity. But the question is, at what speed? Because we have determined that limit. And here I just use this given condition divided by AN on both sides. Because here, first of all, I can deduct from here the limit of 1 over 0. Okay? So from here, I just divide AN plus 1 over AN is equal to 1 plus. So this is what AN to the power of 1 over k. Divided by, so AN at the bottom again. So 1 over AN to the power of 1 plus 1 over k. K is greater than 1, positive integer. So this, like I said, we have to determine this limit. Right? But if we look at this, the limit of 1 over AN is already 0. So is this one. Right? But the question is, if we can determine we raise to the power of 1 plus 1 over k, right? And use Taylor expansion here, because Taylor expansion, 1 plus x to the power of alpha, when x is nearby 0, right, we always have 1 plus alpha times x plus alpha times alpha minus 1 over 2 times x squared, and so on and so forth. So after I tried it, I realized that all I have to do is use these two terms and plus little o of x. And so here the notation little o just represents some, doesn't have to be unique, some infinitesimal, that is some function of x tending towards 0 as x towards x naught, or tending towards 0. That's all I need. And because of that, I say if I let alpha equal to 1 plus 1 over k, I let x equal to 1 over AN to the power of 1 plus 1 over k. Right, that is maybe AN to the power of alpha, just for our convenience. Right, so apply this Taylor expansion with Peano remainder. So we have 1 plus x, that is AN plus 1 over AN, right, to the alpha. Equal 1 plus alpha times x, alpha times and negative alpha, plus little o of x. So here, obviously, I just multiply both sides by AN to the power of alpha, because now I can have AN plus 1 to the power of alpha is equal to AN to the power of alpha plus alpha. Right? This is cancelled out. Plus little o of 1. Right? So this term, right, infinitesimal, tends towards 0. Alpha is a constant. Right? So all I need to, here I can see AN plus 1 to the alpha minus AN to the alpha is equal to alpha plus little o of 1. Right? As x tends towards 0. Right? It already has a limit. Right? So how is this helpful? Right? What does this represent? Right? Because I realize that here I can do if I can say, I'll let this equal to the whole thing equal to Bn. Equal to Bn. So that is A2 to the alpha minus A1 to the alpha. Is B1. A3 to the alpha minus A2 to the alpha is B2. AN plus 1. AN to BN. So when you add them up, so AN plus 1 to the alpha minus A1 to the alpha is equal to B1 all the way to Bn. So how is this helpful? How is this helpful? Because, like I said, this limit is known to be alpha, because this will tend towards 0. So I already know that. Right, so denoted this Bn. So limit Bn to alpha. So divide by n on both sides. Right, divide by n on both sides. Because this is already can be written as n an 1 plus 1 over k to the power of k. Right, that's taking this k out of here. Right, this is alpha. Right, this is already pretty close. Like I said, so knowing Bn tend toward alpha, right? Then this will also tend toward alpha. Right? Then this will tend toward alpha. A1 to the power alpha toward over n tend toward 0. So if we can show that this tend to alpha, then we can immediately show that. Can we show then an plus 1 over tend toward alpha? Right. Then we have that desired limit. Right. Perhaps we'll n plus 1 multiplied by n plus 1 divided by n plus 1. Right. So just so this subscript is consistent with this one. Then n plus 1 over n tend toward 1. So this doesn't really matter. So as long as we can show that this limit is also alpha as this one, right? Alpha is equal to 1 plus 1 over k. Then we can show that an to the alpha over n is also tending toward alpha. So, like I said, given that Bn tending toward alpha, therefore there is a, for any epsilon greater than 0, there is a capital N where little n is capital, as long as little n is bigger than this capital N, we always have the absolute value of Bn minus B is always less than half of epsilon. So the absolute value of B1 all the way to Bn over n minus B. Right, we want to show the limit of this is B. So if this can be small enough, then we're done. Right? So first of all, this can be written as, right, so minus n times B I distribute each b to each one of them, right? Such as b1 minus b, all the way. B capital N minus b. Right? This capital N is this capital N. Plus b capital N plus 1 minus b, all the way to bn minus b. Right, so here, less than or equal to and b1 minus b, b capital N minus b, plus remember, when little n is bigger than this capital N, right? So that's b capital N plus 1, b capital N plus 2, all the way to bn. So their absolute value, like I said, absolute value each absolute value is less than half epsilon. Of course, less than or equal to, because the top here is a constant, positive constant, because once epsilon is given, it's fixed, or you found this capital N that is fixed, so the top has to be fixed positive, right? So denoted as capital M over N, then the plus here. Each absolute value here is less than half epsilon, right? So you have N minus capital N, many of them, over N times half epsilon. Of course, if we let this less than half epsilon, then of course we would require N to be greater than 2N over epsilon, right? Just N over here. So this can be less than half epsilon. And this, if we don't minus this capital N, it becomes larger. You have N over 2N times epsilon, half epsilon. Right? So this whole thing is small enough. Okay? So therefore this limit must be B. Right? So if N is greater than this capital N and M over epsilon. Right? So that meets the definition of the limit. Right? So the limit is really alpha. Right? So this limit is really alpha. So what's that limit? Desired limit. Right? So the desired limit, first of all, can be written as take out the kth power, right? A and k plus 1 over k. 1 plus 1 over k. Right, k. Right, first of all, I have this is alpha. This is alpha. That's tending toward alpha. Right? Tending toward alpha. So tending toward alpha to the k. Right? That is 1 plus 1 over k to the power of k.